All right, so welcome everyone to session 11 on 1111, kind of an odd coincidence. Today we're going to be talking about fixed film processes. I am James Markham. With me today is Valeria Cortez Mora. We're both from the Southwest Environmental Finance Center at the University of New Mexico School of Engineering. And as always, this training is funded by the EPA. Sure, you know the meeting controls by now. Just make sure you're muted while we're doing the presentation. Feel free to unmute to ask questions, though, and you can always use the chat feature at any time. Valeria will be monitoring that and will stop me if she thinks it's necessary. Otherwise, we'll hold questions toward the end. We'll have some Q&A times for both sections of the session today. And then obviously, you're always welcome to reach out to us after hours and ask us questions as well. This whole thing is, of course, designed to assist you with your level 1 or level 2 operator certification. Although, again, some of the topics that we talk about over this series are not listed in the need to knows, but we think they're useful for you from sort of a professional operational basis. As I said, we're on session 11, fixed film media. The next two sessions are going to be very related. We'll be talking about activated sludge in two parts because it's a pretty broad topic. And we're going to take a couple of weeks break, and then we're going to start up with the last half early in the new year. That schedule and the topics will be posted probably by the time we get around to the activated sludge part 2. It's going to be at the same time as the current schedule. Nothing about that has changed, just so we're going to take a couple of weeks off for the winter break because the university's closed, and to let everybody relax a little bit over the holidays. And of course, if you miss anything or you want to review any of the sessions, they are all available on our YouTube channel and our website. I checked yesterday, session 10 is already up there, and it looked like, at least as of yesterday, we'd had 78 reviews. So somebody's going back and checking that out, which is good study practice. Last but not least, make sure you sign in if you're in a group setting, just so that we can make sure that you get credit for attending all of these sessions. And with that, we'll get into the content for today. Brief agenda. We're going to start off with some definitions. We'll do a little bit of history, talk about some design basics and operational parameters, modes of fixed film systems and classifications, and then a little bit on O&M, which is always useful, both from an operational standpoint and a test taking standpoint. But let's start with definitions. First off, what do I actually mean by fixed film? That refers to a film of microorganisms that are typically found on biofilms or slimes on media in a treatment basin, and those microorganisms are the ones that are actually treating the wastewater. So this is a biological process. The main way that fixed film biological processes differ from activated sludge is that in an activated sludge basin, the microorganisms, the wastewater, the aeration, it's all sort of free floating in the treatment basin. And we keep it all mixed up, and the bacteria and other microorganisms in there kind of do what they do, sort of free floating in the basin. Whereas in a fixed film situation, the media in the basin, which is usually rocks or plastic, provides a fixed place for the microorganisms to live. So they're actually attached to the media that's in the basin. Fixed film treatment is actually the oldest form of wastewater treatment that we have. Was basically first recognized around 1890 that aerobic organisms could actually treat wastewater by eating up the carbon in it, the biological oxygen demand. What we're basically doing is microfarming. We're farming bugs. It's a secondary biological treatment process. So, we've got primary separation and settling going on. This is often the next stage. So it's a secondary biological treatment process. Microfarming is one way to think about it, although micro ranching might actually be a little bit more of an appropriate way to think about it, because what we're essentially doing is we are feeding organic material in the wastewater to the microorganisms while providing a home for them on the media. That home gives them access to oxygen from the air, food from the wastewater, and then those microorganisms basically eat that up, grow, multiply. and in the process convert waste in the wastewater into new growth and carbon dioxide. And then, of course, like any herding operation, we have to sort of periodically cull the herd to maintain the growth of the biofilms at a desired level, because if we don't do that, they would essentially just fill up the basin as long as there's food. There are two basic types of fixed film process that we're going to talk about today. The first of which is the trickling filter, which you see here. This is an older style one, typically relatively short, but it basically is designed for removal of biological oxygen demand. And depending on how the setup is done, it could also do nitrification. In trickling filters like the one we see here, we basically distribute the wastewater over the media in a basin so that media in the tank, and by media, I mean the rocks or the plastic media that's inside that the biofilm is living on, it's stationary. It just sits there and the wastewater flows past and the air flows past. So they have a place to live, but the place they live doesn't move. Food comes from the wastewater, and the air either enters from the top or the bottom, depending on the season and how the setup is. And the biological components in there, they do their thing. The other form of fixed film process is what's called a rotating biological contactor, or RBC for short. Um, it's doing the exact same biological process, and you're basically farming or ranching the exact same kind of microorganisms. It's just that the setup is different. In a trickling filter, the media is still, it doesn't move. In a rotating biological contactor, the media, instead of being chunks, is these flat plastic plates, and they spin in the trough. Usually the bottom 40% or so is submerged. The microorganisms grow on the discs. As this picture you can see here, the sort of gray film on there, that's the biofilm. And they get exposed to alternately food and air by being rotated in and out of the basin at a very slow rate. These things, both of these type of operations usually work at around one rotation per minute. So they're fairly slow. But they're basically both use the exact same process, same bacteria. It's just a slightly different setup. Trickling filters are the most common versions that we see in the US. So we'll start with those, because if you're going to be asked about these on an exam, you're more likely to be asked a question about a trickling filter than an RBC. But as we'll see, the same principles, the same formulas for determining operations apply to both. So let's start with trickling filters, which are also sometimes referred to as biofilters or biotowers, depending on where you are. And I want to start out by pointing out that trickling filter is kind of a misnomer, because it implies that they're physically filtering the wastewater in the sense of straining materials out like a coffee filter, and that's not what's happening. They are removing unwanted organics from the wastewater, but they're using metabolic biological processes to do it, not actually physical filtration. So kind of oddly named, but this was sort of the original wastewater treatment form. It was the most common and widely used form of wastewater treatment in the first half of the 20th century. I found references going back to as early as 1908 in Reading, Pennsylvania. There was a 2 million gallon per day facility that was just a giant trickling filter. So they've been around for a really long time. They're relatively low maintenance, and you see them in a variety of applications too, not just in wastewater. If you've been to an aquarium or a pet store and looked at their aquarium setup, or if you happen to have, for example, a saltwater aquarium, I used to have a big 200-gallon one, they have trickling filters in them as well. This is what they look like. It's basically just a small scale version of what's going on at a wastewater treatment plant. Water in this case is coming in through those white pipes at the top. It's being spread out over that light blue mat, trickles down over those bio balls. They're basically just plastic balls with a lot of surface area that promote air movement and provide a lot of surface area for the microorganisms to grow on, and they treat the water as part of their biological process. If you've been to a fish farm or a koi pond, you might have seen a larger one, something like this. Exact same principle, just a slightly larger scale. Water's coming in through that pipe that is going across the top. There's media in there. In this case, it's rocks, and the water trickles down. The microorganisms eat the BOD in the water, and clean it as they go. So they've been around for a really long time, been in use since the 1900s, and they continue to be a really good secondary treatment option in many cases, primarily because they're really easy to maintain. There's just not a lot to do here. As sort of what's going on inside, it's again a secondary biological process, and the biofilms in there typically have two kind of bacteria. They've got aerobic bacteria, which use oxygen in the air like we do to breathe. And they have facultative bacteria as well, which are the bacteria that can use oxygen, dissolved oxygen out of the water or out of the air, but they can also get oxygen chemically. So they can usually live in either aerobic, anoxic, or anaerobic conditions. The kind of bacteria that you do not have in these are the anaerobic bacteria. And if those grow in there, they can cause problems. So what you're going to have here is aerobic and facultative bacteria, and they're generally designed just for BOD removal or BOD removal and nitrification. In other words, turning ammonia into nitrates. Some filters can do both. We'll look at some examples of how those can get set up. Sometimes you use two different filters, one to do the BOD removal and another to do the nitrification. Part of the difference between the bacteria is the bacteria that eat the BOD, they tend to grow relatively fast. So all things being equal, if there's a lot of BOD available, they'll just outcompete the other kinds of nitrifying bacteria. So typically what you have happening is the bacteria that are eating the BOD or metabolizing the BOD are sort of at the front half or the top of the filter, and they're basically taking most of the BOD out, so that the nitrifying bacteria have a much lower BOD concentration and therefore can do their thing without being outcompeted. Really kind of depends on loading rates. We'll talk about those in a little bit. As I said, they've been around for a long time, and the original versions, and there are still some that you see like this, were set up like this. This one is one from 1919 in the UK in Birmingham, and it's a little hard to see because it's an old picture, but basically here you've got giant fields filled with media, rock and slag, or sometimes even wood, with these sort of elaborate pipe and sprinkler systems over them that spray the effluent across the media, and it trickles through and the microbiome does its thing. Sort of the downside of this is they take a lot of space. They were better than, you know, any other thing that was available at the time, but they did take a lot of space. And in this case, you can see there's pretty elaborate pipe networks, and the media is made out of rock. So maintenance is a little bit difficult. Shortly after this was discovered, people started looking at other options, and activated sludge started to come into the fore. And so, you know, these are sort of contemporaneous. And as people did experiments, what they realized was, at least at the time, activated sludge typically had a smaller footprint, gave better effluent quality, and had a lower nuisance factor, because things were tended to be contained. So you didn't necessarily deal with as many smells and bugs that could happen with these large scale trickling filters, or trickling beds, as they were sometimes known. So over time, the activated sludge systems kind of began to dominate. And by the mid-century, they had sort of taken over the market, so to speak, and trickling filters kind of declined. But they've continued to be used, and continued improvements in design, and the development of distribution systems that are better, and particularly the invention of lightweight plastic media to replace the rock, as a media for the microbes to grow on, really increased their capacity, enabled old systems to be retrofitted, and enabled them to meet ever higher effluent standards. So they continue to be really relevant treatment methods. And there are some places that actually use both activated sludge and trickling filters to do different things. The main difference between the two kinds of trickling systems that exist are the distribution systems. The one that I showed you from 1919 is basically one of these fixed nozzle distribution systems where you've got an area or a giant tank, and the nozzles are basically set up like your sprinkler system. They are where they are. They're designed to spray to give an even pattern, so that you get even hydraulic loading. Um, Downside of that is that they're kind of hard to maintain. And again, they take up a broad footprint. More recent versions typically have rotary distribution, and just we're looking from the top down here. So instead of having a fixed pattern of pipes and nozzles, you've got a couple of arms that spin around and distribute the wastewater on top of the media that way. It's much more efficient, and it allows you to do things with, controlling speed and things like that. So basically, with a fixed nozzle system, you're just relying on the design and placement to ensure even distribution, while with a rotary type, basically the arms movement and the size of the orifices or the holes in the arms that the effluent comes out is what ensures the distribution. So two different ways of approaching it. The ones that are currently built pretty much all have rotary distribution setups. A little bit of information for home reading that basically just give you the basics of the differences. The nice thing about the rotating arm option is they can work without a motor, because the pressure of the water being pushed through the holes in the arms is often enough to turn the arm itself. But they can also be motorized, so you can control the rotational speed, which, as we'll see, is kind of important. Either way, whichever system you use, the goal here is uniform loading over the entire tank for optimum efficiency. What you want to avoid is dry spots or dead spots. Um, so again, the rotating arm version is typically what we see and mostly what we're going to cover today. Um, Trickling filter has a couple of different setups. Some of the older ones you see typically look like this. They're relatively short, typically top out at around 10 feet, because they were designed to have rock or slag as a medium. That's pretty heavy stuff. And so once you start stacking loose rock up, you can only go up so high without building enormous structures. So typically they'll be no more than about 10 feet high. The medium in there will be no more than 5 to 7 feet tall. This one happens, or this set happens to be in Belo Horizonte, Brazil. And it shows all the basic pieces. You've got the rotator arm. In this case, it's a 2-arm model that slowly spins around, about 1 rotation per minute. The rock is the black stuff in the media inside. Underneath it, there's a drain so that airflow can get through the media. Pretty straightforward. And then the liquid comes out of the bottom. This is relatively small. These things can actually be enormous. So this is a picture from Stockton where they were building their new treatment plant. And you can see on the left-hand side there, a really, really big 4-arm trickling filter. And if you look at the cars sort of in the middle and on the right-hand side of the picture, it kind of gives you an idea of scale. This thing is probably 40 or 50 feet tall and several hundred feet across. So it's really, really enormous. And with the lighter plastic media, you can get both wider and taller. That being said, pretty much no matter how you build it, their cross section looks more or less the same. The main difference is the height. You've got a sprinkler arm going around the top. You've got a feed pipe that typically goes in and pushes effluent up through the middle. You've got the filter media sort of sitting in a basin that is lifted up off of the ground with a support. And underneath, you've got a collection system with a drain. So these are sort of the 4 basic components that are basic to all trickling filters. So let's talk about media first. Like I said, these started out with rock as the media. And so here's kind of a close-up one of one, I think, that's from the UK. Media typically actually can really be anything. That's one of the things that they noticed early on. You could grow biological films on rock, on bricks, on wood, kind of didn't really matter. The main key was that the pieces were relatively small, sort of in the 2 to 4 inch range, and relatively uniform, because the key to making this work is oxygen. So you have to have void space. You have to have void space for the air to move through, but also for the biofilm to live and for the water to trickle down. The downsides of rock are that A, it's really, really heavy. So it's hard to maintain. If you ever have to move it out of there, it becomes difficult. And the void ratio, so the amount of open space to closed space, typically is around 35 to 50%. So not a lot of open space. And because of that, that limits the area that biofilm can grow on. and it also limits the ventilation area. As I pointed out in the 50s, as we started playing around with plastics and people started coming up with plastic media, that really changed the game. And sort of two different kinds of media, synthetic media or plastic media, were developed. They've got the random dump trickle filter media, which is also what you saw in that sort of fish example I showed you earlier. And these are just pieces of plastic that are designed to have lots of surface area, a lot of airspace, and they typically are designed to sort of make the water splash around as it goes down so you get a little bit more dissolved oxygen. They also developed these plastic cross flow and vertical flow media, like the brick that you see on the right hand side. And you can see that kind of has zigzag channels in it because the idea is that it makes the water kind of slosh around as it moves. But there too, you can see for a given space, there is a lot of surface area. There is a lot of void space. I do want to point out that this picture is kind of deceiving in terms of scale. The random dump media on the left is probably about 3 inches in diameter, whereas the brick on the right is 4 feet long, 2 feet wide, and 2 feet high. So the media that's on the left is typically what is used to retrofit older systems that were originally designed for rock. So, if capacity requirements change, you can remove the rock, replace it with this plastic media, which gives you much more void space, gives you the ability to treat a lot more wastewater than you could with rock because you can just grow a lot more biofilm in there. The nice thing about the plastic cross flow and vertical flow, which basically looks exactly the same, except instead of the channels going down zigzagging, they go straight, is that they're basically like giant Lego blocks. They're self-supporting, they're really light, which enables you in modern designs to build really tall trickling filters. Like I said, the older scale versions are maybe 10 feet max height. New ones can be up to 40 or 50 feet tall. So I've included a table here that gives you some basic information about the different kind of media and sort of the differences. The main thing to note here is that the top two are rock, super, super heavy. You can see the dry weights over on the right-hand side and very limited void ratios and surface areas. So, with rock, you might get 15 to 20 square feet of surface area per cubic foot of media, whereas with some of the plastic versions, you can get almost 70 square feet of surface area. So a lot more room to grow biofilms on them. You've got a much better void ratio, so it allows more liquid to move through, more air to move through, and much, much lighter. So they're a lot easier to maintain or swap out if necessary. And again, you can often tell what kind of media is in a system, or typically tell just by looking at it. If it's short, 10 feet or less, it's probably either got rock media in it or was designed for rock media that's been retrofitted with that random dump plastic media, where basically it's just a bunch of chunks of small media that look the same. With the vertical and cross flow media, it's self-supporting. Like I said, you can have very, very tall structures, 40 feet or more, and they're typically much lighter built too. The short ones typically have brick or concrete sides because the rock is heavy and you need strong walls to hold them in. Whereas with the modern designs, the taller designs, because the media is self-supporting, the sides are typically steel or fiberglass or some other relatively lightweight material because they're basically there just to keep the bugs out, keep the liquid in, and sort of hold everything in place. They're not really there providing much support. So you've got a distribution system, you've got some kind of media, you've got a containment structure, and then underneath the containment structure, you have a drain where all of the treated water works its way out. This is a cross section of sort of a typical setup. Where you're going to have filter media with some sort of grating or spacer to hold it up off the basin. And there will be a series of troughs out there that allow the treated wastewater to move on to the next process, which is typically either another filter or some sort of clarification system. I do want to point out that in particular in the larger systems, under drains sometimes have to be accessed. They can be very large. Remember, they are confined spaces. It is dangerous to work in them. So you want to make sure that you're following all of your safety SOPs, that you're following OSHA confined space rules, because the last thing you want to do is get hurt or trapped in one of these things while you're doing maintenance. Now, I mentioned earlier that they have to have a lot of void space so that oxygen can move through the system because, again, they are mostly aerobic bacteria that we're dealing with here. And this is a less of an issue, closer to the equator out in the islands where there aren't really big temperature swings. Um, from season to season. But here on the continent and in higher latitudes where there are big differences between summer temperatures and winter temperatures, you get some weird things happening with airflow. Um, in the summer, typically, the ambient air temperature is warmer than the effluent. So as air is moving into the tank, it gets cooled down and sinks. So typically in the summer or in a warm climate, you're going to have top to bottom airflow. So basically the air is moving the same direction that the water is, because it's getting cooler, it's getting denser, it sinks. In the winter, we have the exact opposite going on. Typically, the ambient air is colder than the water. So air in the tank gets warmed up by the wastewater that moves through it and it rises. So you get this bottom to top flow pattern. Now, of course, one of the advantages of these systems is that they can be very, very low tech. And you can just sort of let nature run its course. A lot of systems are either retrofitted, and most of the newer systems are actually built with ventilation, mechanical ventilation or blowers, so they can control the airflow. So this is what happens if you don't intervene. Obviously, if you've got mechanical flow air blowers, you can have the air go whatever direction you want. It just uses more energy. So was kind of an interesting phenomenon and something to know, and that's the kind of thing that sometimes shows up on a test. So that's kind of the main components and how they're built. And they're all variations on a theme. The key to running one of these is to understand the design specifications for your particular system. In other words, what range of BOD is it designed to handle? What are the typical BOD concentrations? What are the typical hydraulic flow rates? How much water is typically moving through them? And every system is going to be designed a little bit differently. And every system is going to have some design parameters that you try to stay inside to maintain optimal treatment. So we're going to talk a little bit about those parameters and some design characteristics and efficiency. So two key things that you have to keep track of are what are called the organic loading rate and the hydraulic loading rate. The first one, organic loading rate, is essentially how much food is moving through the system, and the hydraulic loading rate is how much water is moving through the system. And these are thought of separately, even though the food is in the water, and I'll explain that in just a second. But basically, with the organic loading rate, we're looking at how much organic matter, or BOD, is in the system relative to the media volume. So it's food to volume, pounds of BOD over thousands of cubic feet of media. And the hydraulic loading rate, however, is how much water is moving through the system in relation to the surface area. So one is a volumetric view, and the other is an area view. So let's talk about with the organic loading rate first. I'm going to start with a diagram to kind of show you what you consider and what you don't. This is kind of the typical setup. We've got the wastewater moving from left to right. We should be taking a sample so that we know what our concentration is. We've got this primary effluent flow that is working its way through the media. Now, often there is recirculation flow, as there is in a lot of processes, where we're taking some of the treated water and feeding it back into the system. So when we are looking at the organic loading rate, you typically ignore the recirculation flow. It does impact how much BOD is in the water, but not very much. So for typical operational calculations, you ignore those, and the only thing you're paying attention to is what's in blue here. So the concentration, which you're going to get from your lab sample, the volumetric rate, which you're going to get either from doing some math or from a meter that's telling you how much is flowing through, and then your media volume, which is going to be constant. That's just going to be something that you're going to figure out using your volume formulas depending on the size of your tank, and typically these are going to be round these days. So those are the three things that you're going to consider. This is basically what the formula looks like. It looks ridiculously complicated because we're using imperial and metric units. So we're using gallons per day, but we're also using, kilograms and milligrams, and we have to do some uh, uh, conversion factors here. But it's pretty simple when you think about it. Basically, what it is it's the flow in gallons per day converted into liters times your BOD concentration, which is what you're going to get from that lab test, and then some conversions to turn pounds into kilograms, and then that over your volume. This is another version you might see where the two conversion factors are pulled together. So the what in the top line has the 3.785 and 2.25. You multiply those together, you get 8.34. So that's your organic loading rate. It's essentially how much food is in the water divided by area. The other thing that you need to keep track of is the hydraulic loading rate. So you need to know how much food they're getting. You also need to know how much water is going through. The hydraulic loading rate, you actually do have to account for recirculation because recirculation is part of the water that's going through. So you're looking at the media surface area. You are adding together recirculation flow and your raw or primary effluent flow. It's a simpler calculation. It's basically the flow in gallons per day, from your primary, and then whatever you're recirculating divided by the surface area. Pretty straightforward. I'll explain these in a second, kind of what you use these for. Last piece, of course, is the recirculation, keeping track of how much of the treated water you're sort of pushing back through the system. And recirculation is really kind of a key component to operational variability here. It does a lot of things. And what it mainly does is decouples the organic loading from the hydraulic loading, right? So the amount of food that's coming in is more or less constant, but by recirculating treated water, you can essentially change the volume of water that's moving through without impacting the amount of food that's moving through very much. You also use it for other operational procedures. Like I said at the beginning, if you let the biological growth go unchecked, eventually the system would plug up. So you periodically have to kind of rinse it out. Which removes some of the biofilm. And so the recirculation is one of the ways that you do that. You produce hydraulic shear. Basically, you force more water through the system to slough off some of those solids. You can also use it to dilute the wastewater. If you had sort of a random high load of BOD, you could kind of adjust it. You can increase contact time. You can actually use it to sort of reseed the filter with microbes, just kind of like you do in an activated sludge process. Some of the activated sludge goes back to the front to basically sort of reseed the basin, prevent things from drying out. And again, you use the recirculation values to make sure that you're sort of within the hydraulic loading rate specifications. Typically, a system is designed with a specific recirculation ratio or range of ratios in mind. Calculating that is relatively simple. It's just the recirculation flow rate divided by the inflow rate. So for example, if you had 10 million gallons a day being recirculated and your primary influent was 5 million gallons a day, it'd be 10 million over 5 million, which would give you a recirculation value of 2. I'm not giving you a specific ideal range or ideal number to sort of aim for because it's all very, very design specific. So any trickling filter is going to be designed with a specific sort of range of recirculation ratios, a specific hydraulic loading rate range that it can handle, a specific BOD loading rate that it can handle. So the important thing is to know how to calculate them so that you can determine based on your operational parameters whether you're within the scope for your particular design. You don't want to sort of get in the habit of thinking like, oh, at the plant that I work at, recirculation rate is 2, therefore the recirculation rate at all plants is 2. That's very much not the case. You might end up somewhere else that has a slightly different design that has a recirculation ratio that is higher or lower. So the important thing, again, know how to calculate it, know what changing it does, and then read the specs and understand the specs for your particular system. The last sort of main feature that you think about is this thing called the dosing rate. In German, it's called the Spülkraft rate. And to me, that actually makes more sense. I'm half German. And Spülen in German means flushing or rinsing. Um, and this is a very, very odd parameter. But basically, what it quantifies is the intensity at which the influent and circulation flow are being applied to the filter. You can kind of think of it like the rate of fluid coming out of your shower head, right? A high pressure, high shower rate will rinse stuff off very quickly. If you slow things down to a dribble, you don't get as much rinsing off of the soap in the shower. It's sort of the same principle going on in your basin. At a high dosing rate, you're shearing off more biofilm because you've basically got a higher intensity water flushing through the system. It's calculated in inches per pass. It's a little bit of a weird calculation, uh, but it's relatively easy. It's just, you know, how many whatever your hydraulic loading rate is, which is one of the earlier things, converting feet to inches, and then you are looking at the number of arms you have and the speed. So you can affect this a couple of different ways. You could add more arms to your system. Obviously, that's the expensive way to do, but typically the way you address this is you change the hydraulic loading rate and you might change the speed at which those arms are spinning around. And different systems are kind of designed for different BOD load rates. So for example, if you've got a very low BOD load rate under 25, the dosing rate would be somewhere in the 1 to 3 range. And then if you wanted to flush that system, which you typically do once a day, sometimes more, again, depending on the design, sort of get rid of the excess biological growth, you'd run that up to the sort of high end of the range. To sort of flush things off, and those that get caught in the secondary clarifier, everything that got flushed out. And then you'd slow everything back down, reduce the intensity, and the growth cycle would start again. So you can see the higher the BOD rate, obviously the faster the microbes are going to grow. So you need a higher dosing rate and a higher flushing rate to get rid of that additional growth. Last but not least, removal efficiency with all of our processes. Obviously, we have to know how well they're working. This is the same formula you're going to use for other operations in your wastewater treatment. And it's basically, for when we're talking about BOD in specific, it's the concentration of the BOD coming in minus the concentration of the BOD going out divided by that concentration going in, which again is going to let us know, are we removing 50% of the BOD or 80% or 20, again, another important operational parameter. As we'll see, different kinds of trickle filters are designed to have different removal efficiencies. The important thing is to know how to calculate it and what the removal efficiency for your system is supposed to be, so you can determine whether you're sort of within scope or not. A lot of different ways these can be set up. Like I said, sometimes these are set up just to do BOD removal, but they can also do BOD removal and nitrification. And there's sort of two ways to do this. You can do them in single stages or two-stage. A two-stage operation basically splits the two processes into two separate filters. The first one is basically handling the BOD removal, and then you've got very low BOD concentration effluent moving on to the next stage, which is nitrification. Sometimes it's better to do these in separate tanks because, as I mentioned, the BOD, sort of the carbon metabolizing bacteria grow very, very fast, whereas the nitrogen using bacteria tend to grow very slow. So sometimes separating the processes out into separate basins helps you run them better. A lot of the modern systems, the very tall ones, they're designed as single stage operations, and they're basically so big and they can do such an efficient job that basically the carbon eating bacteria are at the top of the tower, the nitrifying bacteria are at the bottom, and so the BOD removal happens in the upper reaches of the tank, and the nitrification happens at the lower. So single stage, two stage, again, it all kind of depends on the design. You can also have series or parallel operation, and this is something that you have in many wastewater processes. A series operation is very much like that first version I showed you, where you've got things happening in sequence. You've got primary effluent being treated. It's going into a tank that is getting rid of BOD. It's going into another tank that might be getting rid of whatever BOD is left, might be doing nitrification, and then you're moving on to a second clarifier. So they're in series, one after the other. You can also have parallel operations, and you're going to see this more often, I think, with the sort of modern setups where you've got an individual trickle filter that can do both processes. And that would look something like this, where you've got primary effluent coming in and the stream is split and it's going to two separate systems that are doing the same process, just essentially next to each other. Parallel operations are often nice for maintenance purposes. And if you've got, significant changes in flow, because you can take one system offline and not have to actually bypass anything. You could just run everything. If you took TF1 off, you could just run everything through TF2 temporarily. Whereas with a series operation, if you have to take one of those steps out, you essentially have to bypass it or figure out something else to do. So series, parallel, important things to remember. Again, that's how you're operating them. Then there's also, as I mentioned, different designs for different BOD concentrations. And those are called filter classifications. So they're basically sort of grouped or classified based on the BOD loading rates that they're designed to do, or in some cases, whether they're just doing BOD, just doing nitrification, or both. So low, intermediate, high, and roughing filters are all referring to types of filters that are primarily designed for BOD removal. And that classification is based on the organic loading rate. And then you have nitrifying filters, and those are basically determined or designated as either BOD plus nitrification or nitrification only. And again, it all depends on how they're set up. But there are some design differences that I want to go through. Again, I don't think you need to memorize these things, but it's good to sort of understand the differences between the classifications and what they're designed to do. So I've got a couple of series of tables here that are comparing plastic media to rock media, just to kind of show you what the differences are. And so in this case, a low rate filter is basically one that's designed to treat water that has a relatively low BOD concentration. So typically, 25 pounds of BOD per thousand cubic feet a day or less. The good thing about these is that they have typically very high BOD removal rates, because there's just not a lot of BOD in the system. And you can see that, for a given setup, the main difference sort of between the plastic media and the rock media is how much fluid you can move through it. So with plastic media, you have much, much higher hydraulic loading rate capabilities than you do with rock media. But the BOD removal rates and the loads that are designed to handle are typically same. Intermediate filters are in that range of 25 to 40 pounds of BOD per day per thousand cubic feet. But as you increase the BOD rate, you also get lower removal rates. So again, you've got much higher loading rates with plastic media, but no matter which version you're using, if you've got a higher organic loading rate, you're going to have typically a lower BOD removal rate. And that's kind of the ratio that you need to understand, or the inference you need to understand. Higher BOD rates typically means, at least with a trickling filter, lower removal rates. High rate filter designed for much higher organic loading rates in that 40 to 100 pounds range. And as you can see, BOD removal rates a little bit lower, 65 to 85%, still pretty good. And in this case, the sort of difference between the hydraulic loading rates is a little bit different. There's quite a lot of overlap sort of in the middle range, with rock media sort of handling hydraulic loading rates maybe up to about 1,000 gallons per day per square foot, and plastic being in the 350 to 2,100 range. So there's quite a lot of overlap. So again, depending on the situation, you can sort of design different kinds of systems that will do what you need. Then there's something called a roughing filter, which is basically there to design to handle like extreme BOD loading rates, 100 to 300 pounds. So, triple what a high rate filter could handle. And as the relationship continues, much higher low BOD loading rate, much lower BOD removal rate. So that's kind of the relationship to remember: high BOD, low removal rate; low BOD, typically high removal rate. And then of course there are the nitrifying filters as well, which are typically using secondary effluent as their source. Of course, there is no real BOD removal going on in these processes. What's going on here is removal of nitrogen, turning it into nitrates. And those percentages are usually pretty good. You can get down to rates of 0.5 milligrams per liter. This is another table that shows you basically the nitrification process in a percentage standpoint. And as you can see, you need relatively low BOD loading rates to get decent nitrification, but you can get up to 95% removal rates with nitrification. So all of these things, as I said, a lot of different parameters to keep track of. All of these really depend on knowing the BOD concentration of your influent. You really cannot adjust these things if you're not doing routine sampling and knowing the typical strength of what's coming in to your system. So like everything else, key to all good operations is a good sampling plan. You want to know what's going in, you want to know what's coming out, so you can control your processes. And the part about becoming a certified operator is that you know how to, or you learn how to tweak those processes so that you can affect the outcome depending on what's coming in. Obviously, not all of these parameters apply to trickling filters. Chlorine residuals don't come into play yet. You're well before the disinfection stage, but this is a table to kind of let you know that typically what you're going to be looking at and where you're going to be doing those samples. So for BOD5, typically, you're going to be sampling that primary effluent that's going into your trickling filter so that you know where it's at. And typical ranges for that primary effluent are going to be sort of in the 100 to 380 milligrams per liter range. And the range that you typically deal with is typically going to inform how you run your system and which of those kinds of filters you have, whether it's a low rate, intermediate rate, or a high rate filter, or a roughing filter, or maybe a couple of those in series. You might actually start out with a roughing filter and then have an intermediate rate filter after that, because the roughing filter has gotten rid of most of the BOD for you. So you got to understand the operational parameters, but like all things, again, sampling is really key. You want to make sure that you're sampling often enough so that you can catch changes and change your operations and adjust them. And different kinds of changes are going to imply that different things are going on in your system. So, for example, if you have high TSS concentrations in the output of your trickling filter, that might indicate that there's like heavy sloughing going on. There's a lot of biomass sloughing on, maybe more than you actually want. Because if you get rid of too much of it, if you rinse too much of the biofilm out, the treatment process slows down. So that's the kind of relationship that over time you will learn. So let's talk about a few of the things that you might run into. Odor is always an issue. Like I mentioned with the big open field versions, that was one of the main objections, that when things went south, you'd have these large fields full of stinky effluent, potentially flies, snails, and other things if they weren't maintained right. So if you have a trickle filter and you are noticing smells from it, there's a couple of things that could be going on. There's several things that are going on. You could have septic influent coming in. So the problem might not actually be the filter itself. It might be processes upstream that aren't doing what they are supposed to, or maybe you had a blockage that took a long time to clear in the collection system and nobody at the plant was warned, and you suddenly had this massive load of septic sewage come in. that's obviously going to have a negative effect on all of the processes downstream if you haven't accounted for those. You might have poor filter ventilation. So maybe you're designed to have a mechanical blower system and the blowers have stopped working, or you've let the biomass accumulate to the point where there's just not enough room for air to move through and things are starting to go anaerobic. Excessive organic loading, same sort of thing. You've let biological overgrowth happen, it's filled up the pore spaces, and now you're not getting airflow. Similarly, you might have dry zones. If the sprayer arms get plugged and you don't see it, you'll have areas where the bacteria basically die off because they're not getting any food or any water, which can create, first anaerobic conditions and then dead zones. Solutions to those, it's all going to kind of depend on what the problem is, but reducing the organic load with recirculation, maybe increasing or adding mechanical airflow, doing some maintenance on your rotary arms. You might have to increase those dosing rates, those sort of points where we increase the intensity to flush more biofilm out regularly to sort of wash out excess biological growth. You might actually have to troubleshoot your primary treatment because, again, just because the problem is manifesting itself in your secondary treatment does not necessarily mean that that's where the cause of the problem is. It could be something upstream. So smells are something that you might run across if maintenance hasn't been done the way it's supposed to. The other things that you might see on these are ponding. So where instead of the water trickling through the filter, it's just sort of forming ponds on the top. This is typically caused by excessive organic loading, which leads to excessive growth. So maybe you've got you know a low range rate filter. And it's designed for less than 25 pounds of BOD per day per 1,000 cubic meters, and for whatever reason suddenly you've got a much higher BOD rate, which has caused the microbes to sort of explode in growth and plug up all the holes and resulting in ponding. This can happen because there's uneven distribution. Again, if the arms are plugged or the distribution orifices are plugged. It could happen if you've got an open top filter and there's just debris that's accumulated on top. Here in Albuquerque, they have some of these, and they're actually got domes over them, and you'll see some of the later pictures that we show where they have domes over them so that they can stop things like leaves falling. This can be an issue in the fall around here. We have all these Siberian elms; they all drop their leaves at the same time, and if they're anywhere near a plant, they could all end up sort of sitting on the top of your media and plugging things up and leading to filter ponding and all the negatives that are associated with that. Like I said, if you're not flushing, in addition to sort of the microbes growing, you can end up with insects and snails and moss and algae in there as well. All of this is basically results in sort of insufficient void space, which then causes the system to break down. So there are a lot of things that you can do depending on what your particular situation is. Again, calibrating those hydraulic loading rates, those organic loading rates, checking your removal efficiency, making changes, slowing down the rotator arm to increase the dosing rate. Same amount of fluids going out, but it's covering less area, so sort of increases the intensity and flushes more off. Sometimes you actually have to flood the entire basin and then drain it to sort of flush out that excessive growth. Or you might actually replace media. Like I said, a lot of older systems that had rock in them are eventually replaced by plastic media. If things get really out of hand, it may be more cost effective to just replace the media than try to do other things. Or you might just need a new treatment unit, an additional unit in series or in parallel to handle the operations. So a lot of operations and maintenance. This is a non-exhaustive list. I did mention that they're low tech, but they are not no tech. And like everything, they do need attention. So, you have to make sure that they're operating correctly. This is sort of a non-exhaustive list, but some of the main things that you need to focus on and sort of the frequency that you would want to look at those as well. Again, I'll let you read those later. So advantages and disadvantages: low energy requirements, typically low maintenance requirements, although not no maintenance. And they can typically treat pretty variable organic loads. That being said, if they're not maintained, they can generate odors. They are sensitive to temperature, particularly if you don't have a mechanical ventilation system. And if you're in a place that has really, really cold weather, the whole system could potentially freeze up. So with that, we got a few poll questions. I think we'll just do the first two here, Valeria, and then we'll do a short session on rotating contractor basins. So What kind of process is it? Is it a preliminary process? Is it a primary process? Or is it a secondary process? Um, we'll give you 30 seconds or so to answer this. If you're in a group, come to a consensus and throw in a vote. All right, looks like we got about half of our folks voting. I'll give you another 20 seconds. Like the exam, if you're not sure, guess. You got a 33% chance of getting it right. All right, going once, going twice. Go ahead and end the poll and show the results for us. Right, it's a secondary process. So it's a biological process. Preliminary treatment is typically a physical process. We're straining things out. That's what's going on at the headworks. Your primary treatments are typically those settlement tanks that are at the beginning of the process, where you're letting a lot of the solids sort of sink out of the system before you go and treat it. And then secondary processes are biological treatment, and that's what this is. On to our next question. All right. So I talked about media earlier. Rock media, random plastic media, and cross-flow media. So random was the one on the left, the sort of uniform looking balls, and the cross-flow media is those bricks. Which of those do you think have the biggest surface area for a given volume? All right, give this another 10 seconds. All right, go ahead and end that and share the results. All right, so the correct answer here is cross-flow media. Most of y'all guessed that it was one of the plastics. The plastic media has significantly more surface area than rock, which is why a lot of the older rock systems have been retrofitted. Random plastic media is sort of the replacement for rock. It is better than rock, has a lot more surface area than rock, but overall, cross-flow media has the most surface area of all of those. All right, so that's enough for the questions. We're going to do a couple of minutes on rotating biological contactors, and then we will open the floor for questions. So RCBs, or actually RBCs, I spelled that wrong there, apologies, were developed in the 50s. And like I said at the beginning, it's the same process with a slightly different setup. Instead of the media being stationary and the water flowing through it, in this case, you've got a basin that the media is sort of rotating in. This is kind of what some of the earlier versions look like. And you've basically got a motor that spins this. You've got a bunch of discs. So instead of plastic media or round media or rocks, you've got these flat discs that the biome grows on. They're stacked along a shaft, and that shaft is sort of semi-submerged in the water like this. You got a sort of a side view schematic and a front view. Typically 35–40% of it's submerged, and basically you're alternating food and air by rotating these pieces around. The processes are basically exactly the same, and the setups are very, very similar to what you might see with trickling filters. They could be run in parallel like these setups. They could be run in series. This is actually both because you've got multiple trains, multiple shafts sort of in series, but then you've got two separate trains. But this also sort of shows you where a trickling filter or an RBC typically sits in the overall process. It's after primary clarification, before secondary clarification and chlorine contact. These things can be rather large, not as big as the other filters. This is sort of a medium-sized one. The biggest ones are about 27 feet long with 25 feet of media stacks. So that thing he's little holding on to, that little sheet, that's the media sheet that the bacteria grows on. And that, once it's installed, just spins in circles in the basin and alternates, food, air, food, air, food, air. This is what they typically look like. This is one up in the central north of the United States. And you can see they're covered, which helps mitigate some of the issues you get with weather changes. And also you notice there's a ton of leaves, trees back there, which probably produce a lot of leaves in the fall. Basic characteristics of these, there's fewer classifications. There's basically standard density and high density. You're looking at the surface area per shaft. So with standard density, you're sort of 110 square feet of area or less per shaft. And those are typically used for BOD removal. And the high density ones that have, a lot of square footage per shaft are typically used for nitrification. So again, these could be in series or in parallel. I want to point out that bottom line, which shows you, in an operational shaft, how much of the weight is actually the biofilm. So, one of those shafts is significantly lighter when you put it in than after it's been operating for a while, because 80% of the weight could actually be biofilm. That being said, same kind of processes and exactly the same parameters you would use to calculate whether you're sort of in the appropriate operational range. You look at organic loading rates, you look at hydraulic loading rates, you look at removal efficiency, you look at recirculation. Same things. Again, your range is going to vary depending on the design. The important thing is to understand how to calculate these, and then again, know where to find the specs for your particular system. But you should have an operations manual that says, if you've got one of these, what range it's supposed to be working at. Like trickling filters, you can do BOD removal and nitrification in the same basin. And this is actually a pretty good visual of it. The left-hand side is doing BOD removal, where you've got that sort of beige bacteria, and the right-hand side is darker, and those are the nitrifying bacteria. So this is one basin doing both processes where you can actually see them. And the nice thing about this is you can get an ammonia nitrogen values reduced to less than 1 milligram per liter. So they're very, very efficient. But the main thing about these, and the big difference between these and trickling filters, is you cannot put high BOD loads through an RBC. If you look at the bottom loads there, you are typically looking at BOD load rates of 3 to 4 pounds of BOD per 1,000 cubic feet per day. Whereas with some of the high rate filters, you might be talking two orders of magnitude more than that, 300 pounds. So these are typically used in small communities, up to maybe 5,000 people, where you've got very, very low organic load rates. Because they just don't work for those other kinds of things. And you're not very likely to see one of these typically in the United States. They're just not that popular here. They're much more used in Europe and other places. And again, the design is for just a whole different scale of BOD concentrations. Got a table in here that gives you some ideas of sort of the hydraulic loading rates and the retention times and the effluent BOD that you're likely to have. As you can see, everything is much, much lower hydraulic loading rates than we're talking about with trickle filters as well. So same process, but designed for different circumstances. Like the other ones, you can operate them in single trains, in multiple trains, in parallel, in series. One of the weird things is you can actually design these to have the flow running parallel to the shaft or perpendicular to the shaft. Again, it's going to be designed based on the quality of wastewater that it's trying to deal with. The one major difference is that if you've got the drums perpendicular, sort of the initial load of BOD coming into the system gets distributed to more biomass because it hits them all edge on. Sort of they're not, it's running through the filter as opposed to running around it. They can be run in a couple of different stages. You can put baffles in them to get different kinds of treatment going on. They've got some limitations, like I said, lower organic loading rates, not as flexible. They're sort of set up for very narrow ranges of BOD removal and sort of slow and steady with not a lot of variation. And obviously, these cannot be used as roughing filters. They would just be completely overwhelmed. So very similar process going on, just different parameters that you're dealing with. And the O&M is very, very similar to what you're looking at with a trickling filter, with the added complication that you need motors to run an RBC. And so you have to look at things like, bearings and shafts and grease main shafts and things like that. But here again, non-exhaustive list, but a list of things that you're typically going to be expected to know how often you might have to look at these things. So with that, I'm a few minutes over. I apologize for going on. We'll skip our last poll question. I will open the floor. If anybody's got any questions, I can try to answer for you. As always, you can reach out to us at any time if you've got questions or need some supplemental materials or need some explanations. I expect the video of this session to be up online within 2 to 3 days if you need to review it. And with that, the floor is open. If you don't have any questions, you're welcome to hang around and see if anybody else does, or we can take off for the rest of the day. And we will see you again in 2 weeks, where we are going to talk about activated sludge, which is a very, very similar process, or biologically, at least what's going on, but a very, very different setup. Kenneth, got your email. We will make sure that you get an invitation so that you can register for these. They happen at the same time every time, but I will make sure that you get a link to the series. And it's one link that will work for the entire series. So just bookmark it or put it in your calendar. They happen every 2 weeks. So we'll get that squared away. And you've got our main email there. If something goes wrong and you don't get that, just reach out and we will take care of you. The more the merrier. Again, pretty dense session today, a lot of information. But thanks for joining us. And like I said, if you've got any additional questions, feel free to reach out if any of it doesn't make sense. Kenneth, glad you liked it. We're trying. We got 15 more to go. And I don't know if you know about this or if it interests you, but on Wednesdays, we have the drinking water track. So every 2 weeks, there's wastewater on Tuesday and drinking water on Wednesday. If you want to join those as well, let me know. I'll make sure you get the links for those as well. Oh, you're in the water series. Awesome. Great. I'll email you the link to this one as soon as we finish up here. All righty. Well, we'll give it a couple more minutes. I don't see any questions, but I will hang out and be the last one to leave the party, so to speak. Thanks for joining us. We'll see you again in 2 weeks. I believe AJ, who is a level 4 operator and has been doing this kind of work for a very long time, will be doing the next 2 sessions. They should be really informative, and he's a great font of information. He's actually the person I go to when I've got questions, even though I've been doing this for a while too. So thanks for joining us. We'll see you again in 2 weeks.